Hello there, and welcome to this sleepy universe zone. Somewhere, right now, deep inside global climate systems, a number is beginning to rise. Not dramatically, not loudly, not in a way that would ever interrupt your day. But the last time this number moved in a pattern like this, tens of millions of people were affected by what followed. And here is the part that makes it difficult to ignore. It is rising again. Slowly, quietly, almost invisibly. And if you have never heard of it before, you are exactly who this story is for. Because tonight, this is not just about distant oceans or abstract science. This is about the hidden systems shaping the world you live in without ever asking for your attention. Right now, if you could look out across the Pacific Ocean, you would see something that appears almost completely normal. Calm waters, no obvious signals, nothing that suggests anything unusual is happening. And yet beneath that surface, something has already begun. Scientists measure the state of this ocean using precise temperature differences. And at the moment, those surface readings appear neutral, balanced, unremarkable, the kind of data point that would usually be ignored. But the deeper models, the ones that track how heat moves beneath the surface, are telling a different story. And not just one model, but multiple independent systems are beginning to point toward the same outcome, a shift toward a strong and potentially extreme phase of a natural climate cycle known as El Nino. And this is where the story becomes something more than technical, because events like this do not stay confined to the ocean. They reorganize rainfall, shift heat across continents, alter storm patterns, influence food production, economies, and the rhythms of daily life across the planet, including where you are right now, even if you have never thought about it before. So if you have ever noticed that some years feel slightly different, warmer nights, heavier rains, longer dry spells, patterns that seem just a little out of place, this is one of the quiet mechanisms behind those changes. And tonight, we are going to explore it together, slowly, gently, without pressure, not to overwhelm you, but to help you see how deeply connected everything really is. And before we go further, if something here resonates with you, even in a quiet way, you can help this reach others simply by leaving a like, not for attention, but for someone else who might need a moment of calm understanding, just like this. And now let us return to the number, because it is small, measured in fractions of a degree, tracking temperature differences in a narrow region of the Pacific, where even the smallest shifts can ripple outward into something much larger. And when that number crosses certain thresholds, scientists begin to classify the state of the ocean. A slight increase becomes a mild event. A larger one becomes strong, and beyond a certain point, it enters a category that has only appeared a few times in modern records, events powerful enough to leave a measurable imprint on the global climate system. What makes this moment unusual is that the ocean surface does not yet reflect what the deeper system is already preparing. Because beneath that calm exterior, heat has been building, stored far below, moving slowly across the ocean through processes that begin long before anything appears at the surface, meaning that by the time most people notice, the outcome is often already in motion. And that leads us to a question that very few people are asking right now. What happens when the ocean looks calm, but the deeper system has already begun to shift? And why does that matter more than what we can see? Over the next chapters, we will follow this signal from the deep ocean to the atmosphere above it, through the patterns it creates across continents, and into the subtle ways it shapes everyday life, not as something to fear, but as something to understand. Because sometimes the most powerful forces shaping our world are the ones that move the slowest and speak the quietest. And for now, all you need to do is settle into the rhythm of it. Because in the next chapter, we will begin with the number itself and why a change of just a few degrees can quietly reshape an entire planet. A difference of just 2 degrees doesn't sound like something that could matter, and yet that is exactly where this story begins to take shape. Because the number we are following is not a temperature by itself. It is a deviation, a small shift away from what is considered normal, measured across a specific region of the Central Pacific Ocean. And under ordinary conditions, that region stays remarkably stable, gently warmed by the sun, balanced by currents, winds, and the slow exchange of heat between ocean and atmosphere. But when that balance begins to tilt, even slightly, the consequences do not stay small. The number scientists track here represents how much warmer or cooler the ocean surface is compared to its long-term average, and most of the time it hovers close to zero, a sign that the system is in equilibrium, neither strongly influencing global weather nor being influenced in return. But when that number rises above a certain threshold and stays there, something fundamental begins to change. Because the ocean is not just water, it is one of the largest reservoirs of energy on Earth. And even a small increase in temperature across such a vast area represents an enormous amount of stored heat. When that heat begins to interact with the atmosphere above it, it alters the way air moves across the planet, shifting patterns of pressure, redirecting winds, and changing where clouds form and where they do not. And this is the moment when a quiet numerical change becomes a global event. The phase we are moving toward is known as El Niño, a naturally occurring climate pattern that emerges when the Central and Eastern Pacific Ocean become warmer than usual. And while the name itself may sound gentle, the process behind it is anything but simple, because it involves a delicate coupling between ocean and atmosphere, a feedback system where each influences the other, sometimes reinforcing the change, sometimes resisting it, and sometimes amplifying it far beyond what the initial signal might suggest. Under normal conditions, strong trade winds push warm surface water westward across the Pacific, allowing cooler water to rise in the east, maintaining a stable gradient. But when those winds weaken or shift, that balance begins to break down. Warm water spreads eastward, the surface warms, and the atmosphere responds by altering circulation patterns that have existed for decades, sometimes even centuries. And once this process begins, it can accelerate in ways that are difficult to reverse. What makes this particularly important is not just the existence of El Niño itself, but the magnitude it can reach. Because not all events are equal. Some remain mild, barely noticeable outside of scientific records, while others grow strong enough to reshape global weather for an entire year or more, influencing rainfall in South Asia, drought conditions in parts of Africa and Australia, and storm patterns across the Americas. And the difference between these outcomes often comes down to how far that small number rises above its threshold. Right now, the projections suggest that we may not be looking at a mild shift, but something potentially much stronger, something that approaches the upper range of what has been observed in the modern era. And this is where the quiet nature of the signal becomes misleading, because there is no sudden moment when everything changes, no clear line between normal and extreme, only a gradual movement that continues until the system crosses into a new state. And here is where it becomes personal, because even if you live far from the Pacific Ocean, even if you have never thought about ocean temperatures before, the effects of this shift can still reach you through the food you eat, the weather you experience, the energy systems that power your daily life, all of it connected in ways that are easy to overlook until something begins to change. And this is why the question is not simply whether El Niño will occur, but how strong it might become, and what that strength means for the systems we rely on without noticing. Because the difference between a moderate event and an extreme one is not just scientific. It is lived, felt, experienced in ways that are often subtle at first and then increasingly difficult to ignore. And yet, despite all of this, there is something even more important to understand, something that most surface-level discussions never fully explain. Because the number we are tracking is only the visible part of a much larger process, a surface signal that reflects what is already happening deep below, where the real energy of the system is stored, and where the future of this event may already be unfolding long before it becomes visible to the world. In the next chapter, we will move beneath the surface into the deeper layers of the ocean, where heat is not just measured but accumulated, where slow-moving waves carry energy across entire basins, and where the true beginning of this story may already be in motion, waiting quietly for the moment it reaches the surface. If the surface of the ocean tells you what is happening now, the deeper layers tell you what is about to happen next. And this is where the story begins to shift in a way that is far less visible, but far more important. Because long before the ocean's surface warms enough to be noticed, the real energy that drives these events is already moving below. Deep beneath the Pacific, sometimes hundreds of meters down, there exists a vast reservoir of warm water, a region where heat has been slowly accumulating over time, carried and stored by currents that most people will never see. And under normal conditions, this heat remains contained, held in place by the balance of winds and ocean circulation, almost like a quiet pressure building in the background. But when that balance begins to change, even slightly, that stored heat does not stay where it is. It begins to move, not as a wave you could see from the shore, not as something dramatic or violent, but as a slow, massive shift in the structure of the ocean itself, something scientists describe as a subsurface wave, traveling across the equator at a steady pace, carrying with it enormous amounts of thermal energy from one side of the ocean to the other. These waves are not fast by human standards, but they are relentless, moving day after day, week after week, it gradually transferring heat from the Western Pacific toward the central and eastern regions. And as they move, they reshape the layers of the ocean, deepening the warm surface layer, lifting or suppressing cooler water below, and preparing the conditions necessary for a surface warming event to emerge. What makes this process so important is that by the time these subsurface changes become visible at the surface, the outcome is often already determined, because the energy required to drive a strong El Niño event does not appear suddenly. It is built, stored, and released over time. And what we are observing now is not just a prediction, but a reflection of conditions that are already in motion. Right now, measurements from ocean monitoring systems indicate that subsurface temperatures across parts of the Pacific are elevated beyond their typical range, not dramatically in a way that would draw immediate attention, but consistently enough to suggest that the ocean has been storing more heat than usual, and that this heat is beginning to organize itself into a pattern that supports further warming. This is why the models are responding the way they are, because they are not only looking at what is happening at the surface, they are incorporating the structure of the ocean below, the distribution of heat at depth, and the pathways along which that heat is likely to travel. And when multiple independent systems detect the same underlying signal, it suggests that the process is not random, but physically grounded in the current state of the ocean. And yet, there is still uncertainty here, because not every buildup of subsurface heat leads to an extreme event. Sometimes the atmosphere resists the change, trade winds strengthen again, and the system returns to a more neutral state, redistributing the energy without allowing it to fully express itself at the surface. And this is one of the key uncertainties that remains in the present situation. But what makes this moment different is not just the presence of subsurface heat, but the timing and structure of it. Because the heat is not only present, it is already moving, already shifting eastward in a way that suggests the system may be progressing toward a more complete release. And once that release reaches the surface, it can begin to interact with the atmosphere in ways that reinforce the warming rather than suppress it. This is the point where the ocean and atmosphere begin to act together, amplifying each other, turning a gradual change into a more pronounced shift. And this interaction is what ultimately determines whether an event remains moderate or becomes something much larger. And so the question is no longer just about the surface temperature or even the subsurface heat itself, but about how the entire system responds once these elements begin to align. Because when the ocean releases its stored energy and the atmosphere responds in a way that reinforces that release, the result is not simply a warmer ocean, but a reorganization of climate patterns across the globe. In the next chapter, we will move from the ocean into the atmosphere to understand how this released heat begins to reshape wind patterns, pressure systems, and rainfall across entire continents, and why that interaction between ocean and air is the moment when a quiet shift becomes something the entire planet can feel. There is a moment in every developing El Niño event when the atmosphere begins to respond, and it is subtle at first, almost impossible to detect without careful measurement. But once it begins, it changes everything, because the atmosphere is not just a passive layer sitting above the ocean. It is an active partner in the system, capable of amplifying or suppressing what the ocean is trying to do. Under normal conditions, The Pacific Ocean and the atmosphere above it are tightly connected through a pattern of winds known as the trade winds, which blow steadily from east to west along the equator, pushing warm surface water toward the western Pacific and allowing cooler water to rise in the east, maintaining the balance that defines a neutral state. But when the ocean begins to warm in the central Pacific, even slightly, that balance starts to weaken, because warmer water changes how heat is released into the atmosphere. And that, in turn, affects the pressure patterns that drive the winds themselves. As the central Pacific warms, rising air shifts eastward, altering the large-scale circulation of the atmosphere, and the trade winds that once maintained the system begin to weaken, sometimes even reversing direction for short periods of time. And when that happens, the process accelerates because weaker winds allow more warm water to move eastward, which leads to further warming, which leads to further weakening of the winds, creating a feedback loop that can drive the system toward a much stronger state. This interaction between ocean and atmosphere is what transforms a gradual buildup of heat into a fully developed El Niño event. And it is also what determines how strong that event will become. Because if the atmosphere responds quickly and reinforces the ocean's warming, the system can intensify rapidly. But if the atmosphere resists, if the winds recover or remain stable, the event may stall or weaken before reaching its full potential. Right now, early indications suggest that the atmosphere may already be beginning to shift in response to the ocean's warming, with subtle changes in wind patterns and convection emerging across parts of the Pacific, not strong enough yet to confirm a fully coupled system, but consistent with the early stages of a developing interaction. These are the kinds of signals that scientists watch closely, because they provide clues about whether the system is likely to continue strengthening or begin to stabilize. And while it is still too early to draw definitive conclusions, the direction of these changes matters, because it tells us whether the ocean and atmosphere are moving toward alignment or remaining out of sync. When alignment occurs, the effects extend far beyond the Pacific itself, because the atmospheric circulation that develops during El Niño influences weather patterns across the entire globe, shifting rainfall belts, altering storm tracks, and redistributing heat in ways that can affect regions thousands of miles away from the source of the change. This is why a temperature shift in one part of the ocean can influence monsoons in Asia, drought conditions in Africa, and storm activity in the Americas, because the atmosphere acts as a bridge, carrying the effects of the ocean's warming across the planet. And yet, even at this stage, there is still uncertainty, because the atmosphere is inherently variable, influenced by many factors beyond the ocean alone, and small differences in how it responds can lead to very different outcomes, which is why forecasts made during this phase must always be treated with caution. But the key point is this: once the atmosphere begins to respond in a consistent way, once the feedback loop between ocean and air begins to strengthen, or the likelihood of a significant event increases, because the system is no longer being driven by a single factor, but by a coupled interaction that can sustain and amplify itself over time. And this brings us closer to the central question of this story, not just whether an El Niño will develop, but how far it might go, And what happens if the conditions that are now forming continue to align in the same direction? In the next chapter, we will begin to place this developing pattern into historical context to understand what similar signals have meant in the past and why certain combinations of ocean and atmospheric conditions have led to outcomes far more significant than the individual components alone might suggest. There is a point in every scientific investigation where the present begins to echo the past, and it is not a perfect repetition, not a simple replay of what has already happened, but a pattern that feels familiar enough to demand attention. And this is where the story begins to deepen, because the signals we are following now are not entirely new. They have appeared before, under different conditions, in a different world, but with consequences that were anything but small. When scientists study large climate events, they do not just look at what is happening now, they look backward, comparing current conditions to historical records, searching for similarities in ocean temperatures, atmospheric responses, and the way different parts of the Earth system interact with each other. And sometimes those comparisons reveal patterns that are difficult to ignore. One of the most important of these patterns comes from the late 19th century, a period when global climate data was far less detailed than it is today, but still rich enough to reconstruct what happened through a combination of observations, historical accounts, and natural records like tree rings and sediment layers. And what those reconstructions show is something remarkable, a period during which multiple regions of the world experienced severe and prolonged drought at the same time, across continents that share no borders, no direct connection, but are linked through the same atmospheric system. This event, which unfolded between 1876 and 1878, is often described as one of the most widespread climate disruptions in recorded history, not because it was the most intense in any single location, but because it was so globally synchronized, affecting regions across Asia, Africa, and the Americas in a way that suggests a common underlying cause. At the center of that cause was a strong El Niño event. But what made it different from other El Niño events was not just its strength, but the way it interacted with other ocean systems at the same time, creating a combination of conditions that amplified its effects far beyond what the Pacific alone might have produced. This is where the idea of multi-basin interaction becomes important, because the climate system is not controlled by a single ocean, but by the combined influence of several major basins, each with its own patterns of variability, each capable of reinforcing or counteracting the others. And when those patterns align in a particular way, the result can be something much larger than the sum of its parts. In the case of the late 19th century event, evidence suggests that the Pacific warming associated with El Niño was accompanied by changes in the Indian Ocean and the Atlantic, creating a configuration that influenced global circulation in a way that led to widespread suppression of rainfall across multiple regions simultaneously. This does not mean that the current situation is identical, because it is not. The world has changed, the climate baseline is different, and the systems we use to observe and understand these processes are far more advanced. But it does mean that there is a precedent, a case where similar types of signals came together in a way that produced a significant global impact. What makes this particularly relevant now is that some of the same elements appear to be developing again, not fully formed, not yet aligned, but moving in directions that resemble parts of that historical configuration. And while this does not guarantee a similar outcome, it raises a question that is difficult to dismiss. What happens when multiple parts of the climate system begin to move in the same direction at the same time? This is not a question of certainty, but of possibility. And understanding that distinction is important because science does not deal in absolute predictions at this level. It deals in probabilities, patterns, and the physical mechanisms that connect them. And what we are seeing now is a set of conditions that increase the probability of a significant event, even if the exact outcome remains uncertain. And so the purpose of looking back is not to suggest that history will repeat itself exactly, but to provide context, to show that the kinds of interactions we are observing now have, in the past, been associated with large-scale changes in the climate system, changes that extended far beyond the ocean itself. In the next chapter, we will take a closer look at those other ocean basins, the Indian Ocean and the Atlantic, and explore how their current state may interact with what is developing in the Pacific. Because the story does not belong to one ocean alone. It belongs to the connections between them. It is easy to think of the Pacific Ocean as the center of this story. And in many ways, it is, because it is the largest ocean basin on Earth and the primary driver of El Niño. But it is not the only player, and focusing on it alone can obscure something more important: the fact that the climate system operates as a network, not a single mechanism, with multiple oceans interacting through the atmosphere in ways that can either balance each other or amplify each other, depending on how they are aligned. One of the key regions in this network is the Indian Ocean, which has its own pattern of variability, known as the Indian Ocean Dipole, a system that describes the difference in temperature between the western and eastern parts of that ocean. And when this dipole enters a positive phase, meaning the western Indian Ocean becomes warmer than the eastern part, it can influence rainfall patterns across South Asia, East Africa, and parts of Australia, often in ways that resemble or reinforce the effects of El Niño. When a strong El Niño and a positive Indian Ocean dipole occur at the same time, their combined influence on atmospheric circulation can lead to more pronounced changes in rainfall, particularly in regions that depend heavily on seasonal patterns such as the monsoon. And this is where the interaction becomes more than just additive, because the atmosphere responds to the combined signal in a way that can amplify the overall effect. At the same time, the Atlantic Ocean plays its own role, particularly the tropical and North Atlantic regions, where sea surface temperatures influence the position of key atmospheric features that govern rainfall and storm development. And when the Atlantic is warmer than usual, it can shift these features in ways that interact with the patterns driven by the Pacific and Indian Oceans, sometimes reinforcing them, sometimes modifying them in ways that are still being studied. What matters here is not the exact mechanism in every detail, but the broader principle that when multiple ocean basins exhibit temperature anomalies in the same general direction. Their combined effect on the atmosphere can produce a more coherent and widespread pattern of change, and this is what scientists refer to as a compound climate event, a situation where several contributing factors align to create an outcome that is larger and more complex than any single factor alone. Right now, observations indicate that the Indian Ocean is showing early signs of a developing temperature gradient consistent with a positive dipole phase. Not yet fully established, not yet certain, but moving in that direction. And at the same time, the Atlantic has remained warmer than average over the past few years, providing another potential source of influence on global circulation patterns. Again, none of this guarantees a specific outcome, because the climate system is highly dynamic and influenced by many variables, but it does suggest that the conditions for interaction are present, and that the Pacific is not acting in isolation. This is why the question we are asking is not simply how strong the El Niño event might become, but how it might interact with these other systems if they continue to evolve in the same direction, because it is that interaction, that alignment across basins, that has the potential to shape the global response in a more significant way. And this brings us back to the idea introduced earlier, that the most important developments in the climate system are often not the most obvious ones, but the ones that emerge from the combination of multiple subtle changes, each of which might seem minor on its own, but together form a pattern that is much more consequential. In the next chapter, we will begin to explore what those combined effects look like in practice, how shifts in ocean temperatures translate into real changes in weather patterns across different regions of the world, and why those changes can sometimes occur simultaneously in places that seem completely unrelated at first glance. There is a moment when separate changes stop being separate, when patterns that once seemed independent begin to align, and the climate system starts to behave less like a collection of parts and more like a single, interconnected whole. And this is where the story becomes both more subtle and more powerful, because what happens next is not driven by one ocean or one region, but by the way the entire system responds together. When the Pacific warms during El Niño, it does not simply heat the air above it. It shifts where energy is released into the atmosphere, and that shift alters global circulation patterns, changing where air rises and where it sinks. And because rising air is associated with clouds and rainfall, while sinking air suppresses them, the result is a redistribution of moisture across the planet. Regions that normally receive steady rainfall may experience less, while others may receive more, and these changes can extend far beyond the Pacific itself, influencing weather patterns across continents that are thousands of miles away. When the Indian Ocean enters a positive dipole phase at the same time, it reinforces some of these shifts, particularly over regions like South Asia and East Africa, where seasonal rainfall depends on delicate balances in atmospheric circulation. And when the Atlantic remains warmer than average, it adds another layer of influence, adjusting the position of key atmospheric features that guide moisture and storm development. What emerges from this alignment is not a single event, but a coordinated pattern, one that can produce similar outcomes across regions that would otherwise seem unconnected, such as drought conditions appearing simultaneously in different parts of the world, or shifts in rainfall occurring across multiple continents during the same season. This is what makes compound climate events so significant, because they do not operate in isolation. They synchronize effects across the system, and that synchronization can amplify the overall impact in ways that are not immediately obvious from any single component. And yet, even as this process unfolds, it does so quietly, without a single defining moment, without a clear signal that marks the transition from one state to another, only a gradual alignment that becomes more apparent over time as patterns begin to reinforce each other and the system settles into a new configuration. This is why early signals can be easy to overlook, because they do not appear dramatic on their own. They require context, an understanding of how different parts of the system interact, and how those interactions can evolve. Right now, the signals we are observing suggest that such an alignment is possible. Not certain, not inevitable, but possible. And that possibility is what makes this moment worth paying attention to. Because when the system begins to move in a coordinated way, the effects are not confined to one region. They extend across the globe, shaping weather, influencing ecosystems, and altering the conditions that people experience in their daily lives. And this leads us to an important realization that the climate system does not operate in isolated pieces, but as a connected network, where changes in one part can influence outcomes in another, often in ways that are difficult to trace without careful observation. In the next chapter, we will begin to translate these large-scale patterns into real-world effects, exploring how shifts in circulation lead to changes in rainfall, temperature, and seasonal behavior across different regions, and why those changes can sometimes occur all at once rather than gradually over time. When the atmosphere begins to reorganize in response to warming oceans, one of the first things it changes is where rain falls and where it doesn't. And while this might seem like a simple shift, it is one of the most powerful ways the climate system affects life on Earth, because rainfall patterns determine agriculture, water availability, ecosystems, and the stability of entire regions. Under normal conditions, rainfall is distributed according to well-established patterns, with certain regions receiving consistent seasonal rains, while others remain dry. And these patterns are shaped by large-scale circulation systems that move moisture through the atmosphere in predictable ways. But when those circulation systems shift even slightly, the distribution of rainfall changes with them. During a strong El Niño event, the center of tropical rainfall often moves eastward across the Pacific, following the warmer waters. And as this happens, regions that typically receive moisture from these systems may find themselves under descending air instead, where clouds struggle to form and rainfall is reduced. This is why parts of South and Southeast Asia, which rely heavily on seasonal monsoon rains, can experience weaker or delayed rainfall during certain phases of El Niño, while regions in the Eastern Pacific and parts of the Americas may see increased precipitation. When additional factors, such as a positive Indian Ocean dipole, align with this shift, the effect on rainfall can become more pronounced, because the same regions may experience reduced moisture from multiple directions at once, reinforcing the drying effect and making it more persistent. At the same time, warmer conditions in the Atlantic can influence rainfall patterns across Africa and the Americas, shifting the position of rain-bearing systems and altering the timing and intensity of seasonal precipitation. The result is a pattern where multiple regions may experience changes in rainfall at the same time, some becoming wetter, others drier, but all influenced by the same underlying shift in atmospheric circulation. What makes this particularly significant is not just the presence of these changes, but their timing. Because when rainfall patterns shift during critical growing seasons, the effects can extend beyond weather into agriculture and food production, influencing crop yields and water availability in ways that can take months or even years to fully unfold. And yet, these changes do not happen all at once. They begin gradually, often appearing as small deviations from expected patterns, a slightly delayed rainy season, a period of dryness where rain would normally occur, subtle signals that may not seem significant at first, but can accumulate over time into something much larger. This is why understanding the underlying mechanisms is so important, because it allows us to see these changes not as isolated anomalies, but as part of a broader pattern, one that connects ocean temperatures, atmospheric circulation, and the distribution of rainfall across the planet. And even now, as these processes are beginning to take shape, there is still uncertainty, and because the exact distribution of rainfall depends on how the system evolves, how strongly the ocean and atmosphere couple, and how other factors interact with the developing pattern. But the direction of change is already becoming clearer, suggesting that the system is moving toward a state where rainfall patterns will be reorganized on a large scale. In the next chapter, we will look at how these shifts in rainfall and temperature translate into real-world conditions on land, exploring how ecosystems, agriculture, and human systems respond to these changes, and why even small shifts in climate patterns can have far-reaching consequences over time, long before anyone notices a pattern on a global map. The first real effects of these shifts begin quietly on land, in soil, in crops, in ecosystems that depend on the steady rhythm of rainfall and temperature. And what makes this stage so important is that it does not arrive all at once. It unfolds gradually, often in ways that feel disconnected at first. A slightly drier season here, a delayed planting there, small variations that seem local, temporary, easy to dismiss, until they begin to align. When rainfall patterns shift, even by a modest amount, the land responds immediately, because soil moisture depends not only on how much rain falls, but when it falls, how quickly it evaporates, and how plants use it. And when that balance changes, the effects ripple outward. In regions that rely on consistent seasonal rains, even a short delay can alter planting cycles, affecting crop growth at critical stages, while in drier regions, a small reduction in rainfall can push conditions closer to drought, not as a sudden event, but as a slow depletion of moisture over time. At the same time, temperature plays a role that is just as important, because warmer air increases evaporation, drawing moisture out of the soil more quickly. And when this happens alongside reduced rainfall, the effect is amplified, creating conditions where the land dries faster than it can recover. These processes are not dramatic in the moment. They do not announce themselves. They accumulate, building gradually until the difference becomes visible. Crops begin to show stress. Vegetation changes color. Water sources decline. And what began as a subtle shift becomes something more tangible. And yet, even at this stage, the connection to the ocean may not be obvious because the changes are experienced locally through weather and environment, not through global climate patterns. And this is why the link between ocean conditions and land responses can be difficult to perceive without stepping back and looking at the system as a whole. What makes the current situation worth following is not just the possibility of change, but the potential for those changes to occur across multiple regions at the same time. Because when similar patterns emerge in different parts of the world, they are less likely to be random and more likely to reflect a shared underlying cause. This is where the idea of synchronization becomes important again, because if multiple regions begin to experience shifts in rainfall and temperature simultaneously, it suggests that the atmospheric circulation patterns driving those changes are acting on a global scale, rather than being confined to a single location. And when that happens, the effects can extend beyond individual ecosystems, influencing agricultural production, water availability, and the stability of systems that depend on predictable climate conditions. But even now, it is important to remember that these outcomes are not fixed. They depend on how the system continues to evolve, how strong the underlying signals become, and how different regions respond to the changes as they unfold. Because the climate system is not a single path, but a range of possibilities shaped by the interaction of many factors. In the next chapter, we will begin to explore how these land-based changes connect to larger human systems, not as immediate disruptions, but as gradual influences that can shape economies, food supply, and the way societies respond to shifting environmental conditions over time. When changes begin in the natural world, they do not stay there. They move outward, gradually intersecting with the systems people rely on every day. And this transition from environmental shift to human impact is often subtle, unfolding over time rather than in a single moment. But it is in this transition that the full significance of these patterns becomes clear. Agriculture is one of the first systems to respond, because it depends directly on climate conditions, on rainfall arriving at the right time, on temperatures remaining within certain ranges. And when those conditions shift, even slightly, the effects can accumulate across growing seasons, influencing yields in ways that may not be immediately visible, but become apparent over time. When multiple regions experience similar shifts at once, the impact can extend beyond local agriculture into broader supply systems, because food production is not isolated, it is interconnected, with different regions contributing to global supply in different ways. And when those contributions change simultaneously, the system must adjust. This adjustment does not happen instantly. It unfolds through a series of responses, changes in planting decisions, shifts in trade patterns, adaptations in water management, all of which take time and depend on the information available to those making decisions. And this is where the importance of early signals becomes clear, Well, it's because understanding what is happening in the climate system allows for preparation, not in a dramatic sense, but in small, practical ways, adjustments that can reduce the impact of change before it becomes more significant. At the same time, energy systems can be influenced by shifts in temperature and weather patterns, as demand changes with heat and cooling needs, and water systems respond to variations in rainfall and evaporation, creating a network of interconnected responses that extend beyond the environment itself. What is important to recognize is that these systems are designed to operate within certain ranges of variability. They can adapt to change, but only within limits. And when multiple changes occur at once, or when conditions move beyond those expected ranges, the process of adaptation becomes more complex. This does not mean that the system fails, but it does mean that it must adjust, and those adjustments can take time, resources, and coordination, particularly when they occur across regions simultaneously. And yet, even as these processes unfold, they do so quietly, without drawing attention, because most of the changes happen gradually, through small shifts that accumulate over time, rather than through sudden events. This is why the connection between a changing ocean and daily life can feel distant, even though it is real, because the pathway from one to the other is not direct. It moves through layers of interaction, each one subtle on its own, but together forming a pattern that becomes more visible as it develops. In the next chapter, we will return to the climate system itself to explore how these patterns continue to evolve over time and what indicators scientists use to determine whether the current signals are strengthening, stabilizing, or beginning to shift in a different direction, because the story is still unfolding and the outcome depends on how these processes continue to interact in the months ahead. At a certain point, what begins as a faint signal either fades into the background or becomes clearer, and this stage, where uncertainty slowly gives way to definition, is one of the most closely watched phases in the evolution of a climate event, because it is here that scientists begin to understand not just what might happen, but what is increasingly likely to happen. In the early stages, the system is filled with noise, small fluctuations in wind, temperature, and pressure that can obscure the underlying trend, making it difficult to distinguish between a temporary variation and a developing pattern. But as time passes, the stronger signals begin to stand out, emerging from that noise in ways that can be measured more consistently. One of the key indicators scientists monitor is the behavior of the trade winds across the Pacific, because these winds play a central role in maintaining or disrupting the balance of the ocean atmosphere system. And when they begin to weaken in a sustained way, it often signals that the coupling between ocean and atmosphere is strengthening, allowing the warming pattern to reinforce itself. At the same time, surface temperatures in the central Pacific are observed for signs of consistent increase, not just short-term spikes, but a steady upward movement that persists over weeks and months, indicating that the underlying heat from below is reaching the surface and beginning to influence the atmosphere above. Another important factor is the spread of predictions across different climate models, because early on, models may disagree widely, reflecting the uncertainty in the system. But as the signal strengthens, their outputs often begin to converge, pointing toward a narrower range of outcomes. And this convergence is one of the ways scientists assess confidence in a forecast. Right now, the situation remains in this transitional phase, where the signal is present but still evolving, where some indicators are beginning to align while others remain variable. And this is why the coming weeks and months are so important, and because they will determine whether the current pattern continues to strengthen or begins to shift in a different direction. What makes this process particularly interesting is that it does not happen all at once. There is no single moment when certainty appears, only a gradual accumulation of evidence, each piece adding to the overall picture, until the pattern becomes clear enough to act upon with greater confidence. And yet, even as clarity increases, uncertainty does not disappear entirely, because the climate system remains dynamic, influenced by interactions that can still alter the course of events, which is why forecasts are always framed in terms of probability rather than certainty. But the key point is this: the signal is already present, and the system is moving towards a state where that signal will either strengthen or weaken, and the direction it takes will shape the conditions that follow. In the next chapter, we will explore one of the most important factors influencing this outcome: the seasonal timing of these processes, and why the time of year plays a critical role in determining how accurately we can predict what comes next. There is a time each year when the climate system becomes more difficult to read, a period when signals that might otherwise be clear are partially obscured by natural variability. And this period, often referred to as a seasonal barrier in prediction, is one of the most challenging aspects of forecasting events like El Niño, because it introduces a level of uncertainty that cannot be easily removed. During this time, which typically occurs in the transition between late winter and early summer in the Northern Hemisphere, the interaction between ocean and atmosphere weakens slightly, reducing the strength of the coupling that allows signals to stand out. And as a result, short-term variations in the atmosphere can temporarily mask or distort the underlying trends in the ocean. This does not mean that the underlying processes stop. The subsurface heat continues to move. The ocean continues to evolve, but the atmosphere becomes less responsive in a consistent way, making it harder to determine how the system will develop in the months ahead. Historically, this period has been associated with lower forecast skill, meaning that predictions made during this time are more likely to change as new data becomes available. And this is why scientists approach this phase with caution, not because the models are unreliable, but because the system itself is less predictable during this window. What makes the current situation notable is that despite this seasonal uncertainty, the signal we are observing is still emerging with a degree of consistency, suggesting that the underlying forcing may be strong enough to persist even through this period of increased variability. This does not eliminate uncertainty, but it does provide additional context, indicating that the processes driving the current pattern are not easily disrupted by short-term fluctuations. As the system moves beyond this seasonal phase and into a period where ocean-atmosphere coupling strengthens again, the signal is expected to become clearer, allowing for more confident assessment of its likely trajectory, and this transition is one of the key moments to watch because it often determines whether an event will continue to develop or begin to fade. For now, the presence of this uncertainty is an important reminder that the outcome is not fixed, that multiple scenarios remain possible, and that the system is still in the process of revealing its direction. In the next chapter, we will look at how past events have behaved during this phase, examining cases where early signals strengthened into significant events and others where they diminished, and what those examples can tell us about the range of possibilities that lie ahead. There have been times when the ocean seemed ready, when the heat was in place, when the early signals pointed in one direction, and yet the outcome turned out to be something else entirely. And these moments are just as important to understand as the events that fully develop, because they reveal the limits of prediction and the delicate balance within the climate system. One of the most well-known examples occurred in the mid-2000s, when conditions across the Pacific began to resemble the early stages of a strong warming event. Subsurface heat was present, waves of warm water were moving eastward, and early forecasts suggested the possibility of a significant El Niño. But as the months passed, the atmosphere did not respond in the way that had been expected. The trade winds did not weaken enough to sustain the process, and the system stabilized before reaching the intensity that many models had projected. What this showed was not a failure of science, but a reflection of the complexity of the system itself. Because the ocean can store energy, it can begin to release that energy, but without the cooperation of the atmosphere, the process may not fully develop. And this is one of the key uncertainties that remains in every forecast. The relationship between ocean and atmosphere is not one-sided. It is a negotiation, a feedback loop that can either amplify or dampen the initial signal, and small differences in how that interaction unfolds can lead to very different outcomes. This is why even when multiple models point toward a strong event, there is always a range of possibilities because the system has pathways that can diverge depending on how conditions evolve over time. In the current situation, the presence of subsurface heat and the early signs of atmospheric response suggest that the system may be moving toward a more complete coupling, but it is still within a phase where alternative outcomes remain possible, and this is where careful observation becomes essential, because the difference between a strengthening event and a weakening one may depend on changes that occur over a relatively short period of time. What makes this particularly important is that the consequences of these different outcomes are not the same, because a moderate event may produce noticeable but manageable changes in weather patterns, while a stronger event can have more widespread and pronounced effects. And understanding which path the system is taking allows for better preparation and response. But even as we consider these possibilities, it is important to maintain perspective, because uncertainty is not a flaw in the process. It is a natural part of understanding a system as complex as the Earth's climate, and acknowledging that uncertainty allows for a more accurate and balanced view of what lies ahead. In the next chapter, we will explore the range of outcomes that scientists consider plausible based on current observations, not as fixed predictions, but as scenarios that reflect the different ways the system might evolve and what each of those scenarios could mean in practice. When scientists look at the current state of the ocean and atmosphere, they do not see a single outcome. They see a range of possibilities, each one shaped by the same initial conditions, but diverging based on how the system evolves over time. And this range is what defines the forecast, and not as a prediction of certainty, but as a set of scenarios that reflect different paths the system could take. The most likely scenario, based on current data, is that the warming in the Central Pacific continues to develop into a strong El Niño event, one that reaches a level capable of influencing global weather patterns in a noticeable way. And this scenario is supported by the presence of subsurface heat, the early indications of atmospheric response, and the convergence of multiple models toward a similar outcome. In this case, the effects would likely include shifts in rainfall patterns across key regions, changes in temperature distributions, and a reorganization of atmospheric circulation that influences weather on a global scale. But within this scenario, there is still variation, because the exact strength of the event, the timing of its peak, and the way it interacts with other climate systems can all influence the final outcome. A second scenario involves a moderate event, where the warming continues, but does not reach the higher thresholds associated with more extreme impacts. And in this case, the effects would still be present, but less pronounced, with regional changes in weather patterns that are noticeable, but not as widespread or intense. A third scenario, though less likely, involves the possibility that the system stabilizes before fully developing, similar to past cases where early signals weakened over time. And in this outcome, the effects would be limited, with the ocean returning toward a more neutral state, without producing a significant event. Each of these scenarios is consistent with the current understanding of the system, and each reflects a different balance between the forces driving the warming and those that may counteract it. And what determines which scenario unfolds is the interaction between ocean and atmosphere over the coming months. What makes this range of outcomes particularly important is that it highlights the role of probability in climate science, because rather than focusing on a single expected result, scientists consider the likelihood of different possibilities, allowing for a more flexible and adaptive approach to understanding and responding to change. This approach acknowledges that while we cannot predict every detail with certainty, we can identify patterns, assess risks, and prepare for outcomes that are more likely, while remaining aware of those that are less so. And this brings us back to the central idea that the climate system is not static. It is dynamic, evolving over time, influenced by interactions that can shift its trajectory in subtle ways. And understanding those interactions is key to interpreting what the current signals mean. In the next chapter, we will begin to explore how these potential outcomes translate into real-world impacts, not in abstract terms, but in the specific ways they influence temperature, weather, and the conditions people experience across different regions, and why even moderate changes in the system can have meaningful effects over time. A shift in global temperature is often described in numbers, fractions of a degree, averages across the planet, values that seem abstract and distant. But those numbers do not remain abstract. They translate into lived experience, into the way heat feels on a summer afternoon, into the length of a warm night, into the persistence of a season that lingers just a little longer than expected. And when an El Niño event develops, it adds another layer to that experience. Strong warming in the Pacific does not simply stay over the ocean. It releases heat into the atmosphere, and that heat is redistributed across the globe, raising average temperatures in ways that can be measured not just by instruments, but by people through changes in daily conditions. Historically, years influenced by strong El Niño events tend to be among the warmest on record, not because the event itself creates new heat, but because it brings existing heat from the ocean into the atmosphere, making it more immediately felt. And when this happens on top of an already warmer global baseline, the effect can become more noticeable. Days may feel slightly hotter, nights may cool less efficiently, and periods of warmth may persist longer than usual, creating conditions that can influence comfort, energy use, and the way ecosystems respond to seasonal cycles. These changes do not occur uniformly. Some regions may experience more pronounced warming than others, depending on how atmospheric circulation redistributes the heat. But the overall pattern tends toward an increase in global average temperature during the peak of the event. What is important to understand is that these changes are not isolated. They interact with other aspects of the climate system, influencing evaporation, soil moisture, and the formation of weather systems, which creating a chain of effects that extend beyond temperature alone. Warmer air holds more moisture, which can intensify rainfall in regions where precipitation increases, while at the same time, higher temperatures can accelerate drying in regions where rainfall decreases, amplifying the contrast between wet and dry conditions. This dual effect is one of the defining features of El Niño, the ability to produce both increased rainfall and increased dryness in different parts of the world at the same time, depending on how circulation patterns shift. And yet, even as these changes occur, they do so gradually, often blending into the natural variability of the climate, making them difficult to distinguish without careful observation, because the difference between one year and the next may not be dramatic, but it can be consistent enough to influence trends over time. This is why the impact of temperature changes is best understood not as a single event, but as part of a broader pattern, one that unfolds over months and seasons, shaping the conditions that define how people experience their environment. In the next chapter, we will look more closely at how these temperature changes interact with extreme events, exploring how the same processes that raise average temperatures can also influence the intensity and frequency of weather events, and why those connections are an important part of understanding the full impact of a developing El Niño. While average conditions provide one way of understanding climate, it is often the extremes that define its impact. The days that are much hotter than usual, the storms that bring more rain than expected, the dry periods that last longer than they should, and these extremes are influenced by the same underlying processes that shape the average, but in ways that can be more noticeable and sometimes more disruptive. When an El Niño event develops, it alters the distribution of heat and moisture across the atmosphere, and this redistribution can create conditions that favor certain types of extremes in different regions, depending on how the circulation patterns shift. In areas where rainfall increases, the additional moisture in the atmosphere can lead to heavier precipitation events, because warmer air can hold more water vapor, allowing storms to release larger amounts of rain over shorter periods of time. And this can increase the likelihood of flooding, particularly in regions where infrastructure or natural systems are sensitive to rapid changes in water levels. At the same time, in regions where rainfall decreases, the combination of reduced precipitation and higher temperatures can intensify dry conditions, leading to longer and more severe droughts, especially when soil moisture is already limited, and this can affect not only agriculture, but also water resources and ecosystems that depend on consistent moisture availability. These contrasting effects, increased intensity of wet conditions in some areas and increased intensity of dry conditions in others, are a hallmark of the changes associated with El Niño, and they highlight the way the climate system redistributes rather than uniformly increases or decreases environmental conditions. Another important aspect is the influence on storm patterns, particularly in regions where atmospheric circulation shifts can alter the paths that storms typically follow, sometimes steering them toward new areas or changing their frequency. And while the exact details depend on many factors, the general principle is that changes in large-scale circulation can influence the behavior of weather systems in ways that extend beyond local conditions. What makes this particularly relevant is that these changes do not occur in isolation. They interact with existing conditions, meaning that the impact of an extreme event depends not only on the event itself, but on the state of the environment before it occurs. And this is why the same type of event can have different effects in different regions or at different times. And yet, and even with these complexities, there is a consistent thread that shifts in the ocean can influence the atmosphere in ways that affect extremes, shaping the conditions under which weather events develop and evolve. Understanding this connection does not eliminate uncertainty, but it provides a framework for interpreting how and why certain patterns emerge and how they might change as the system evolves. In the next chapter, we'll begin to explore how these environmental changes connect to broader systems, looking at how shifts in temperature and precipitation influence resources, infrastructure, and the way societies adapt to changing conditions over time. There is a quiet assumption built into many of the systems that surround us, an expectation that conditions will remain within a certain range, that seasons will follow familiar patterns, that changes will occur gradually enough to be managed without disruption. And most of the time, that assumption holds, because the climate system, despite its complexity, often behaves in ways that are relatively stable over short periods of time. But when underlying patterns begin to shift, even slightly, that stability is tested, not through sudden collapse, but through gradual pressure on systems that were designed with certain expectations in mind. Water systems are one of the clearest examples because they rely on predictable cycles of rainfall, storage, and distribution. And when those cycles change, even modestly, the balance between supply and demand can be affected. A delay in seasonal rains can reduce the amount of water entering reservoirs, while higher temperatures can increase evaporation, reducing stored water more quickly. And these changes can combine to create conditions where resources become more limited, not because of a single event, but because of a series of small deviations that accumulate over time. Agriculture responds in a similar way, because crops are adapted to specific ranges of temperature and moisture, and when those ranges shift, even slightly, it can influence growth, timing, and yield, requiring adjustments in planting schedules, irrigation, and crop selection, all of which take time and depend on the ability to anticipate change. Energy systems also reflect this dependence on stability, as demand for heating and cooling responds directly to temperature, and changes in weather patterns can alter both the amount and timing of energy use, creating challenges for systems that must balance supply and demand continuously. What connects all of these examples is not vulnerability in a dramatic sense, but sensitivity to variation. The way systems respond to changes that move them outside their expected range, even if those changes are relatively small. This sensitivity is not inherently negative. It is part of how systems are optimized for efficiency under normal conditions, but it does mean that when multiple changes occur at once, or when conditions shift in ways that were not anticipated, the process of adaptation becomes more complex. And this is where the broader significance of climate patterns emerges, not as isolated events, but as influences that shape the conditions under which these systems operate, and creating a background context that can either support stability or introduce variability. Right now, the signals we are observing suggest that the background conditions may be shifting, not in a way that guarantees disruption, but in a way that introduces the potential for change across multiple systems at the same time. And understanding that potential is an important part of understanding what lies ahead. In the next chapter, we will explore how these interconnected systems respond when changes occur simultaneously across different regions, and why the timing of those changes can influence the overall impact in ways that are not immediately obvious. A single change in one place can often be managed, adjusted for, or absorbed by systems that are designed with some degree of flexibility. But when similar changes begin to occur across multiple regions at the same time, the situation becomes more complex, not because any one change is overwhelming, but because the ability to compensate from one region to another becomes limited. This idea of simultaneity is central to understanding why certain climate patterns have broader effects, because it is not just the magnitude of change that matters, but the extent to which those changes are synchronized across the system. In the context of a developing El Niño, the shifts in atmospheric circulation can influence rainfall and temperature patterns across multiple continents, and when these shifts align with conditions in other ocean basins, the resulting effects can occur in different regions during overlapping time periods. For example, if reduced rainfall occurs in more than one major agricultural region during the same growing season, the impact on production can be greater than if those changes occurred at different times, because there is less opportunity for one region to offset the conditions in another. Similarly, if increased rainfall affects multiple regions simultaneously, it can influence water management systems, infrastructure, and ecosystems in ways that require coordinated responses rather than isolated adjustments. What makes this particularly important is that many global systems are interconnected, relying on the ability to move resources, information, and support from one area to another. And when multiple areas experience similar conditions at the same time, that flexibility can be reduced. This does not mean that systems fail, but it does mean that they must operate under more constrained conditions, where adjustments require greater coordination and may take longer to implement. And yet, even in these situations, the changes often unfold gradually, not as sudden events, but as overlapping patterns that become more apparent over time, as data accumulates and the extent of the alignment becomes clearer. This gradual unfolding can make it difficult to recognize the full scope of the change in the moment, because each individual effect may seem manageable on its own, but together they form a pattern that is more significant. This is why the concept of synchronization is so important, because it provides a way of understanding how multiple small changes can combine into a larger system-level effect. even when each change is relatively modest. Right now, Oshu, the conditions we are observing suggest the possibility of such alignment, not yet fully realized, not yet certain, but moving in a direction where multiple factors could begin to act together. And it is this possibility that makes the current situation worth following, because it represents a point where the system could shift from isolated variability to coordinated change. In the next chapter, we will return to the scientific perspective, exploring how researchers study these patterns using historical data and modern models, and how they assess the likelihood of different outcomes based on the signals that are currently emerging. Understanding something as vast and complex as the climate system requires a different way of seeing, not just observing what is happening now, but placing it within a framework of past events, physical laws, and carefully tested models. And this is where the scientific process becomes essential, because it provides the tools to interpret signals that would otherwise seem abstract or disconnected. Scientists do not rely on a single measurement or a single model. They combine multiple sources of data, satellite observations, ocean sensors, atmospheric readings, and historical records to build a picture of how the system is evolving. And then they use models, mathematical representations of physical processes, to simulate how those conditions might develop over time. These models are not perfect, but they are grounded in the fundamental principles of physics, describing how heat moves through the ocean, how air responds to temperature differences, and how these interactions create the patterns we observe as weather and climate. When multiple models, developed independently and based on different assumptions, begin to produce similar outcomes, it suggests that the underlying signal is strong enough to be detected across different approaches. And this convergence is one of the key indicators scientists use to assess confidence in a forecast. At the same time, historical data provides context, showing how similar conditions have evolved in the past. And while no two events are identical, patterns can emerge that help guide expectations, highlighting which combinations of factors have led to stronger or weaker outcomes. This combination of observation, modeling, and historical comparison allows scientists to move beyond simple description and toward understanding, identifying not just what is happening, but why it is happening and what it might mean. Right now, this process is actively unfolding, with researchers analyzing the current state of the ocean and atmosphere, comparing it to past events, and refining models as new data becomes available. And what they are seeing is a system that is beginning to organize itself in a way that supports further development, though not without uncertainty. This uncertainty is not a limitation, but a reflection of the system's complexity, because the climate is influenced by many interacting factors, some of which can change quickly, altering the course of events in ways that are difficult to predict precisely. And yet, even within this uncertainty, there are signals that stand out, patterns that repeat, and physical mechanisms that provide a basis for understanding how the system behaves. This is what allows scientists to speak in terms of probability, to say that certain outcomes are more likely than others based on current conditions, even if they cannot predict every detail. In the next chapter, we will explore how these scientific insights are translated into forecasts, how probabilities are communicated, and what it means to interpret a prediction not as a certainty, but as a range of possible outcomes shaped by the current state of the system. When most people hear a forecast, it is often interpreted as a prediction, a statement about what will happen. But in climate science, A forecast is something more nuanced. It is a description of likelihood, a way of expressing how probable different outcomes are based on the information available at a given moment. This distinction is important because it shapes how we understand and respond to the information, not as a fixed outcome, but as a set of possibilities that can guide awareness and preparation. A forecast might indicate a high probability of a strong El Niño event, meaning that the conditions currently observed are consistent with those that have led to such events in the past, and that models, when given these conditions, tend to produce similar outcomes, but it does not guarantee that the event will unfold exactly as projected, because the system can still evolve in ways that alter the trajectory. This probabilistic approach allows scientists to incorporate uncertainty directly into their analysis, acknowledging that while certain pathways are more likely, others remain possible, and that the range of outcomes reflects the complexity of the system rather than a lack of understanding. One of the ways this is communicated is through ensemble forecasts, where multiple simulations are run with slightly different initial conditions, creating a range of possible futures, and the distribution of these outcomes provides insight into both the most likely scenario and the degree of uncertainty. When the results cluster closely together, it suggests higher confidence, while a wider spread indicates greater uncertainty. And both pieces of information are valuable because they help interpret not just what might happen, but how certain we can be about it. Right now, the forecasts indicate a tendency toward continued warming in the Central Pacific, with a significant portion of simulations pointing toward a strong event. But they also show a range of outcomes, reflecting the possibility that the system could evolve differently depending on how the ocean and atmosphere interact in the coming months. And this is why forecasts are updated regularly as new data becomes available and the system moves through different phases, allowing scientists to refine their understanding and adjust probabilities accordingly. What is important to recognize is that a forecast is not a static statement. It is part of an ongoing process, a way of tracking how the system is evolving over time and how our understanding of it changes as new information is incorporated. And this process is what allows us to move from uncertainty toward clarity, not all at once, but gradually as evidence accumulates and patterns become more defined. In the next chapter, we will begin to look ahead, exploring how the current signals might develop over the coming months. What indicators will be most important to watch, and how the unfolding of these processes will shape the conditions that define the next stage of this story. There is a window of time in every developing climate event when the future begins to reveal itself more clearly, not all at once, but through a series of signals that either strengthen or fade. And right now, we are entering that window. Over the next 60 days, several key indicators will determine the direction this system takes. And while they may seem technical at first, they are in fact simple expressions of how the ocean and atmosphere interact. The first is the behavior of the trade winds across the Central Pacific, because these winds act as both a driver and a regulator of ocean conditions. And when they weaken in a sustained way, they allow warm water to continue moving eastward, reinforcing the warming pattern that defines El Niño. If those winds remain weak or weaken further, it suggests that the system is becoming more strongly coupled, meaning the ocean and atmosphere are beginning to work together rather than counteract each other. The second indicator is the rate of surface warming in the Nino 3.4 region, not just whether temperatures increase, but how consistently they do so over time. Because a steady rise indicates that the underlying heat from the subsurface is continuing to emerge, while irregular fluctuations may suggest that the system is still influenced by short-term variability. The third is the evolution of subsurface heat itself, particularly in the eastern Pacific, where the arrival of warm water from the west can signal that the energy driving the event is fully in motion. And this is often one of the clearest signs that the system is progressing toward a more developed state. Together, these indicators provide a way of reading the system as it evolves, not as a single measurement, but as a pattern of changes that reveal whether the underlying processes are strengthening or stabilizing. What makes this period so important is that it represents a transition, a movement from early signals toward more defined conditions. And as this transition unfolds, the uncertainty that currently surrounds the forecast will begin to narrow, allowing for a clearer understanding of what lies ahead. And yet, even as clarity increases, it is important to remember that the system remains dynamic, capable of shifting in response to factors that may not yet be fully understood, which is why careful observation during this time is essential. In the next chapter, we will explore how this transition from uncertainty to clarity has played out in past events, looking at the moments when early signals either strengthened into major climate patterns or diminished into more moderate outcomes, and what those examples can tell us about the path we are currently observing. At some point, a developing pattern stops being a possibility and becomes a reality, not because of a single defining moment, but because the accumulation of evidence reaches a level where the direction of the system is no longer ambiguous. And this transition is one of the most important phases in understanding climate events, because it marks the shift from prediction to observation. In past El Niño events, this transition often occurs as the ocean and atmosphere become fully coupled. When the warming at the surface is sustained, the trade winds remain weakened, and the atmospheric circulation adjusts in a way that reinforces the ocean's state, creating a feedback loop that maintains and amplifies the pattern. Once this coupling is established, the system tends to follow a more predictable trajectory, with the event continuing to develop toward its peak before eventually declining. And this progression can be tracked through a combination of temperature measurements, wind patterns, and atmospheric indicators. What distinguishes stronger events from weaker ones is not just the presence of this coupling, but its intensity and persistence, because a more strongly coupled system is able to sustain the feedback loop for a longer period, allowing the warming to reach higher levels and influence a broader range of atmospheric processes. Right now, we are approaching the stage where this transition could begin to take place, where the signals that have been developing beneath the surface and within the atmosphere may align in a way that confirms the direction of the event. And when that happens, the focus of observation shifts from whether the event will occur to how strong it will become and what its impacts might be. This is also the point at which the connection between ocean conditions and global weather patterns becomes more apparent, as the changes in atmospheric circulation begin to produce measurable effects across different regions, not as isolated anomalies, but as part of a coherent pattern that reflects the underlying state of the system. And yet, even as the pattern becomes clearer, it does not unfold uniformly. Different regions respond in different ways, and the timing and intensity of those responses can vary, which is why the effects of a global climate event are experienced differently depending on location. What remains consistent, however, is the underlying mechanism, the way in which the ocean and atmosphere interact to redistribute heat and moisture across the planet, shaping the conditions that define weather and climate over the course of the event. In the next chapter, we will begin to explore how these emerging patterns interact with longer-term trends in the climate system, and how the current state of global temperature and ocean heat content may influence the way this event develops compared to those in the past. Every climate event begins from a baseline, a starting condition that defines how the system behaves before any additional changes take place. And one of the most important differences between the present and the past is that this baseline is no longer the same. Over the past century, global temperatures have increased, not in a uniform or constant way, but in a gradual upward trend that has shifted the average state of both the atmosphere and the ocean. And this shift matters because it changes how events like El Niño unfold. When the ocean warms during an El Niño event, it is not warming from the same starting point as it did decades ago. It is building on top of an already elevated temperature, and this means that the absolute values reached during the event can be higher even if the relative change remains similar. This difference may seem small, but it has important implications because many processes in the climate system respond not just to changes, but to absolute thresholds, points at which certain conditions become more likely or more intense. For example, warmer air can hold more moisture, which can influence the intensity of rainfall in regions where precipitation increases, while higher baseline temperatures can contribute to more rapid drying in areas where rainfall decreases, amplifying the effects of the underlying pattern. In the ocean, higher baseline temperatures mean that the amount of heat available to be released into the atmosphere is greater, potentially influencing the strength of the interaction between ocean and atmosphere and the way energy is distributed across the system. This does not mean that every El Niño event will be stronger than those in the past, because the development of each event depends on many factors, but it does mean that the context in which these events occur has changed, and that this context can influence their characteristics and impacts. What makes this particularly important is that the climate system does not respond linearly to changes. Small increases in temperature can lead to disproportionate changes in certain processes, especially those that involve thresholds or feedback loops. And this is why understanding the baseline is essential to understanding the event itself. Right now, the system we are observing is not only evolving in response to the processes we have already discussed, but doing so within a climate that is warmer than it was during many of the historical events used for comparison. And this introduces an additional layer of complexity because it means that past analogues, while useful, may not fully capture the range of possible outcomes. In the next chapter, we will explore how this shifted baseline interacts with the patterns we have been following, and how the combination of current conditions and ongoing changes may influence the way this event develops compared to those that came before. The climate system is shaped by patterns that repeat over time, but those patterns do not exist in isolation. They are influenced by the conditions in which they occur, and when those conditions change, the behavior of the patterns can change as well. This is what makes the current situation particularly interesting, because it involves the interaction of a well-known climate pattern, El Niño, with a set of background conditions that are different from those in which many past events occurred. When scientists look at historical records, They often use past events as analogues, comparing current conditions to those that have produced similar outcomes in the past. And this approach is valuable because it provides a framework for understanding how the system might behave. But it also has limitations because no two events occur under exactly the same conditions. The current baseline of global temperature, ocean heat content, and atmospheric compositions introduces differences that can influence how the pattern unfolds, potentially altering its intensity, duration, or the distribution of its effects. For example, a similar level of ocean warming in the Pacific might lead to different atmospheric responses if the surrounding regions are warmer than they were in the past, because the gradients that drive circulation patterns are affected by the relative differences between regions, not just their absolute values. Similarly, the interaction between different ocean basins may be influenced by the current state of those basins, meaning that the way the Pacific, Indian, and Atlantic Oceans interact during this event may not be identical to past cases, even if some of the individual components appear similar. This does not mean that past events are no longer relevant, but it does mean that they must be interpreted with an understanding of the differences in context, and recognizing that the system is evolving and that those changes can influence outcomes in subtle ways. What remains consistent, however, is the underlying physics, the principles that govern how heat moves through the ocean, how the atmosphere responds to temperature differences, and how these interactions create the patterns we observe. And it is these principles that allow scientists to extend their understanding beyond simple comparisons, using models and observations to explore how known processes behave under new conditions. Right now, this combination of familiar patterns and changing context creates a situation that is both recognizable and unique, a convergence of elements that has been seen before, but not in exactly the same form. And this is why careful observation and analysis are so important, because they allow us to understand not just what is happening, but how it fits into the broader evolution of the climate system. In the next chapter, we will begin to explore how these evolving conditions influence the way the system moves toward its peak, looking at the processes that determine how strong the event becomes and how long it is likely to last before transitioning back toward a more neutral state. Every El Niño event follows a general arc, a gradual rise, a period of maximum intensity, and then a decline. But within that arc, the details can vary in important ways, and understanding how the system moves toward its peak is key to understanding what kind of event it may become. The build-up phase is driven by the continued release of heat from the ocean into the atmosphere, a process that depends on both the availability of that heat and the ability of the atmosphere to respond in a way that reinforces the warming. And when these conditions align, the system can intensify relatively quickly, moving from a developing state to a strong event over the course of several months. One of the defining features of this phase is acceleration, not in the sense of sudden change, but in the way small increases begin to compound, as warmer surface temperatures lead to further weakening of the trade winds, which in turn allows more warm water to move eastward, reinforcing the pattern. This feedback loop is what drives the system toward its peak, and the strength of this loop often determines how high that peak will be. And because a more efficient coupling between ocean and atmosphere allows the process to sustain itself for longer, reaching higher levels of warming before stabilizing. At the same time, the distribution of heat within the ocean plays an important role, because the amount of energy available for release is not uniform, and regions with greater subsurface heat content can contribute more strongly to the development of the event, particularly as that heat reaches the surface. What makes this stage particularly important is that it is also when the broader impacts begin to take shape, as the strengthening of the ocean-atmosphere interaction leads to more pronounced shifts in atmospheric circulation, and these shifts begin to influence weather patterns across different regions. However, the path to the peak is not always smooth. There can be periods where the system appears to pause, where temperatures stabilize or fluctuate, reflecting the influence of short-term variability or temporary changes in atmospheric conditions, and these pauses can create uncertainty about how the event will evolve. But if the underlying conditions remain favorable, if the subsurface heat continues to support surface warming and the atmosphere continues to respond in a reinforcing way, the system tends to resume its progression toward a peak. Right now, the signals we are observing suggest that this build-up phase may already be underway, though not yet fully realized, and the coming months will be critical in determining how far the system progresses along this path. In the next chapter, we will explore what happens at the peak of an El Niño event, how the system stabilizes at its maximum intensity, and what factors determine how long that peak is sustained before the system begins to transition into its next phase. At the peak of an El Niño event, the ocean and atmosphere reach a state of temporary balance, where the processes driving the warming are at their strongest and the effects on global circulation are most pronounced. And this is the point at which the influence of the event is felt most clearly across the planet. During this phase, sea surface temperatures in the central and eastern Pacific are at their highest relative to normal, and the atmospheric circulation has adjusted to this new state, with shifts in wind patterns, pressure systems, and rainfall distribution that reflect the altered balance of energy in the system. And this is when the characteristic impacts of El Niño become most evident. Changes in precipitation patterns across tropical and subtropical regions, alterations in storm tracks, and shifts in temperature distributions that can influence weather conditions across a wide range of latitudes. The duration of this peak phase can vary, sometimes lasting for several months, and during this time, the system maintains a relatively stable configuration, even as underlying processes continue to evolve. What determines the length and intensity of the peak is the balance between the forces sustaining the warming and those working to dissipate it, because while the feedback loop between ocean and atmosphere drives the system toward its peak, other processes, such as the gradual redistribution of heat within the ocean and changes in wind patterns, begin to counteract that warming. Over time, these opposing forces lead to a weakening of the feedback loop, and the system begins to transition away from its peak state. But the timing of this transition can vary depending on the strength of the initial conditions and the interactions within the system. During the peak, the global effects are often most visible, as the reorganization of atmospheric circulation influences weather patterns across multiple regions simultaneously, creating a coherent pattern that reflects the underlying state of the climate system. This is also when the connection between ocean conditions and land-based impacts becomes most apparent, as changes in rainfall and temperature translate into observable effects in ecosystems, agriculture, and human systems. And yet, even at this stage, the system is not static, and it continues to evolve, with subtle changes that signal the beginning of the next phase, the gradual decline of the event, and the return toward a more neutral state. In the next chapter, we will explore how this transition occurs, how the system moves away from its peak, and what happens to the heat that was released during the event as it is redistributed within the ocean and atmosphere, setting the stage for future cycles. No climate state lasts forever, and even at its peak, an El Niño event is already beginning the process of its own decline. Not abruptly, not in a way that can be clearly seen from one moment to the next, but gradually, through a redistribution of the very energy that brought it into existence. As the ocean releases heat into the atmosphere over time, the reservoir of warm water that sustained the event begins to diminish, and at the same time, changes in wind patterns start to re-establish the conditions that favor a return toward balance. The trade winds, which had weakened during the build-up and peak phases, often begin to strengthen again, pushing surface waters westward and allowing cooler water to rise in the eastern Pacific, reintroducing the gradient that defines a neutral state. This process is not instantaneous. It unfolds over weeks and months, and during this period, the system may still exhibit characteristics of El Niño, even as the underlying dynamics are shifting. What makes this transition particularly interesting is that it is not simply a reversal of what came before, because the system has been altered by the event itself. Heat has been redistributed, the atmospheric patterns have adjusted, and the ocean's internal structure has changed, all of which influence how the system evolves as it moves away from its peak. In some cases, the transition leads directly back to neutral conditions, while in others, it may continue into an opposite phase, known as La Niña, where cooler than average conditions develop in the central and eastern Pacific, creating a different set of atmospheric responses and global effects. This possibility depends on how the ocean and atmosphere interact during the decline, and whether the processes that restore the system to balance overshoot that balance, pushing it into a new state. Right now, this phase is still far ahead, but understanding it provides a sense of the full cycle, showing that what we are observing is part of a larger pattern, one that includes not just the development and peak of an event, but also its resolution and the conditions that follow. And as the system moves through this cycle, it carries forward the effects of what has occurred, influencing subsequent conditions in ways that can extend beyond the event itself. In the next chapter, we will step back from the physical processes and consider a broader perspective, exploring how cycles like El Niño fit into the larger rhythms of the Earth's climate system, and how understanding these rhythms can provide insight into both the past and the future. If you step back far enough, beyond individual events, beyond years and even decades, the climate system begins to reveal itself as a series of rhythms, patterns that repeat over time, not with perfect regularity, but with a structure that reflects the underlying physics of the Earth system. El Niño is one of these rhythms, part of a larger cycle that alternates between different phases, each influencing the distribution of heat and moisture across the planet in its own way. And this cycle is not isolated. It interacts with other patterns, both within the oceans and in the atmosphere, creating a complex web of variability that shapes the climate we experience. These rhythms are not driven by a single force, but by the interaction of many, the rotation of the Earth, the distribution of land and ocean, the movement of heat through the atmosphere and the sea, and the influence of external factors such as solar energy, all combining to create a system that is dynamic, interconnected, and constantly evolving. And what makes these patterns particularly fascinating is that they operate across different timescales, some unfolding over months, like El Niño, others over years or even decades. And understanding how these timescales interact is key to understanding the climate as a whole. For example, longer-term trends can influence the baseline conditions in which shorter-term events occur, altering their characteristics and impacts, while shorter-term events can contribute to the variability observed within longer-term patterns. This interplay creates a system that is both predictable in its general behavior and variable in its specific outcomes, allowing for patterns to be recognized even as individual events differ from one another. In the context of what we are observing now, this perspective provides a sense of continuity, showing that the current signals are part of a larger sequence, not an isolated occurrence, and that by understanding the rhythms of the system, we can better interpret the meaning of the changes we are seeing. It also highlights the importance of observation because each cycle provides new information, new data that can be used to refine our understanding and improve our ability to anticipate future changes. And yet, even with this knowledge, there remains an element of uncertainty because the system is influenced by many factors, some of which are still being studied. And this uncertainty is part of what makes the study of climate both challenging and deeply engaging. In the next chapter, we will bring this broader perspective back to the present moment, exploring how the current signals fit within these rhythms and what they suggest about the path the system may take in the months ahead. After following the patterns, the physics, the history, and the possible paths forward, we arrive back at the present moment. And what makes this moment unique is not that something dramatic has already happened, but that something may be in the process of forming. The ocean at the surface still appears relatively calm. Measurements remain close to neutral, and to most observers, there is no clear indication that anything significant is underway. But beneath that surface, the signals we have been tracing continue to evolve. Subsurface heat remains elevated, moving gradually across the Pacific, and early atmospheric responses are beginning to align with that movement, not strongly enough yet to confirm a fully developed system, but consistently enough to suggest that the underlying processes are active. This is the stage where the system is poised between possibilities, where the same set of conditions could lead to different outcomes depending on how the next phase unfolds. And this is why the present moment is defined more by potential than by certainty. Scientists observing these patterns are not simply asking whether an event will occur. They are asking how the different elements we have discussed will interact, whether the ocean and atmosphere will continue to move toward alignment, whether the signals from different regions will reinforce each other, and how the broader context of current climate conditions will influence the result. These are not questions that can be answered immediately because the system itself is still in motion, still evolving, and the answers will emerge over time as the signals become clearer. What we can say is that the ingredients for a significant event are present, not in a complete form, not yet assembled into a single outcome, but existing in a configuration that has, in the past, led to notable changes in the climate system. This does not mean that the same outcome will occur again, because each event is shaped by its own context, but it does mean that the current situation is worth understanding, worth observing, and worth following as it develops. And so this chapter is not about conclusion, but about awareness, about recognizing that the system is in a state of transition, and that the quiet signals we have been exploring are part of a larger process that is still unfolding. In the next chapter, we will begin to bring together everything we have discussed, not as a final answer, but as a way of understanding what it means to observe a system in motion, and how that understanding can shape the way we think about change, uncertainty, and the connections that define the world we live in. There is a natural tendency to look for conclusions, to want a clear answer to the question of what will happen. But the nature of the system we have been exploring does not always allow for that kind of certainty, and perhaps more importantly, it does not require it. Understanding the climate system is not about predicting every detail. It is about recognizing patterns, understanding processes, and seeing how different parts of the system interact over time. And this kind of understanding does not need to be urgent or overwhelming. It can be quiet and gradual and reflective. What we have followed through these chapters is a process: the movement of heat through the ocean, the response of the atmosphere, the alignment of different systems, and the way these elements combine to create patterns that influence the world on a global scale. And while the details of the outcome remain uncertain, the structure of the process is clear. The ocean stores energy, the atmosphere responds, patterns emerge, and those patterns shape conditions across the planet. And this cycle repeats, not exactly, but in ways that can be understood through observation and study. What makes this knowledge valuable is not just its ability to inform predictions, but its ability to provide context, to help us see the connections between distant parts of the system and to understand how changes in one area can influence outcomes in another. It also offers a way of approaching uncertainty that is grounded in awareness rather than concern, recognizing that not every question has an immediate answer, and that understanding often comes from following the process as it unfolds, rather than trying to define it too early. In this sense, the story we have been exploring is not just about a specific event, but about the way we observe and interpret change, about how we move from noticing a small signal to understanding its place within a larger system. And as we continue into the final chapters, the focus will shift from explanation to reflection, from the mechanics of the system to the broader perspective it offers, and the quiet realization that even the most complex processes can be understood step by step, simply by paying attention. Uncertainty often feels like something to resolve, something to eliminate as quickly as possible. But in systems as vast as the climate, uncertainty is not an obstacle. It is a natural state, a reflection of complexity rather than confusion. The ocean does not move in straight lines. The atmosphere does not respond in perfect symmetry. And the interaction between them is shaped by countless variables, some measurable, some still being explored. And this means that even the most advanced models can only describe probabilities, not certainties. But there is a different way to experience uncertainty, not as tension, but as space, as the quiet openness that exists before something becomes fully defined. Right now, the signals we have followed are still in that space, forming, shifting, moving towards something that has not yet fully emerged. And there is value in observing that process without rushing it, in allowing the system to reveal itself at its own pace. This does not mean ignoring the signals. It means holding them with awareness, recognizing their meaning without forcing them into a fixed conclusion. Scientists do this naturally, working with ranges, updating models, refining understanding as new data arrives, and in doing so, they demonstrate a way of thinking that is both precise and patient, grounded in evidence but open to change. For the listener, this perspective offers a different relationship with information, one that does not demand immediate answers, but instead invites a slower engagement, a recognition that understanding unfolds over time, just as the climate itself does. And in that unfolding, there is a kind of quiet clarity, not because everything is known, but because the process of knowing is itself steady and continuous. In the next chapter, we will step even further back, moving beyond the mechanics and probabilities and exploring what it means to observe a system of this scale, to consider the broader perspective that comes from seeing the Earth not as separate parts, but as a connected whole. From a distance, the Earth appears as a single system, a sphere of water, air, and land, moving together through space. And while we experience it in fragments, weather in one place, seasons in another, the underlying reality is one of connection, where changes in one region can influence conditions across vast distances. The ocean currents that carry heat from the tropics toward the poles, and the atmospheric circulation that moves moisture across continents, the patterns that link the Pacific, Indian, and Atlantic Oceans, all of these are expressions of a system that is unified, even as it appears divided. El Niño is one example of this unity, a pattern that begins in one part of the ocean but extends its influence across the globe, not through direct contact, but through the invisible pathways of air and energy that connect distant regions. When we follow these pathways, we begin to see that the climate is not a collection of isolated events, but a network of interactions, where each change is part of a larger flow. This perspective changes the way we think about cause and effect, moving from simple relationships to more complex patterns, where multiple factors combine, reinforce, or counteract each other, creating outcomes that reflect the system as a whole rather than any single part. It also highlights the importance of scale, because what seems small at one level can have broader implications when viewed within the larger system, and what appears distant can still be connected through processes that operate beyond immediate perception. Right now, the patterns we are observing are part of this larger network, signals that move through the system, influencing and being influenced by other components. And understanding them requires seeing not just the individual pieces, but the connections between them. And in that understanding, there is a sense of continuity, a recognition that the processes shaping the present are part of the same system that has shaped the past and will continue to shape the future. In the next chapter, we will begin to bring this perspective inward, exploring how observing these connections can influence the way we think, the way we interpret change, and the way we relate to systems that are larger than ourselves. There is a moment, sometimes subtle, when a collection of separate observations begins to feel like a pattern, when what once seemed like isolated pieces starts to connect into something more coherent. And this shift is not just about information, it is about perception. At the beginning, the details can feel scattered: numbers, temperatures, currents, winds. But as we follow them, as we give them time and attention, they begin to organize themselves into something that makes sense, not because they have changed, but because the way we see them has changed. This is what it means to learn a system, not memorizing facts, but recognizing relationships, understanding how one part leads to another, how a shift in one place echoes somewhere else, and how the whole moves together even when the pieces seem distant. In the case of the climate, this way of seeing reveals something profound, that the planet is not random but patterned, not predictable in every detail, but structured in its behavior, governed by principles that create consistency even within variability. When you understand that warm water moves eastward in waves beneath the surface, that winds respond to temperature differences, that circulation patterns shift in response to those changes, you begin to see the system not as a collection of events, but as a process, something unfolding over time with its own internal logic. And once you see that process, it becomes easier to follow, easier to interpret, because you are no longer reacting to individual signals. You are observing how those signals fit within a larger flow. Right now, the pattern we have been tracing is still forming, not yet complete, not yet resolved, but recognizable enough to follow. And that recognition is what allows us to engage with it in a meaningful way, not as passive observers, but as participants in the act of understanding. And as we continue, the focus begins to shift from the external system to the internal experience of observing it, because there is something about following a process like this that changes how we think, how we relate to uncertainty, and how we find clarity in complexity. In the next chapter, we will explore that shift, looking at how the act of observation itself becomes part of the experience, and how understanding a system can influence the way we see not just the world, but our place within it. As we follow something as vast and intricate as the climate system, something else begins to happen quietly in the background. The mind that is observing starts to change its rhythm. At first, there is effort, trying to understand, trying to connect the pieces. But over time, that effort softens, and observation becomes more natural, more fluid, less about forcing understanding, and more about allowing it to emerge. This shift is subtle, but important, because it reflects a different way of engaging with complexity, one that does not rely on control, but on attention. The climate does not need to be simplified to be understood. It needs to be observed with patience, with a willingness to let patterns reveal themselves gradually. And when we do that, the experience becomes less about solving a problem and more about witnessing a process. There is a quiet steadiness in that kind of observation, a sense that even though the system is vast and constantly changing, it is also coherent, moving according to principles that can be followed if we give them time. This steadiness can extend beyond the subject itself influencing how we approach other kinds of uncertainty, showing that not everything needs to be resolved immediately. That clarity can come from staying with a process rather than rushing toward an answer. In this way, the act of understanding the climate becomes something more than an intellectual exercise. It becomes a practice of attention, a way of training the mind to notice patterns, to hold complexity without becoming overwhelmed, and to find a kind of calm within the flow of information. And as this perspective deepens, the boundary between observer and system begins to feel less rigid, not in a literal sense, but in the recognition that we are part of the same world we are observing, influenced by the same processes, connected through the same networks of energy and matter. This does not make the system smaller, but it makes our relationship to it more grounded, more integrated. And in that integration, there is a sense of perspective, a way of seeing that is both expansive and centered at the same time. In the next chapter, we will move toward the closing of this journey, bringing together the patterns, the processes, and the perspective we have developed, and allowing the story to settle into something that can be held quietly, without urgency, and as part of a larger understanding. At a certain point, the need to follow every detail begins to soften, and what remains is the shape of the story itself, not the individual measurements or signals, but the arc they form when seen together. The ocean storing heat, the currents carrying it across vast distances, the atmosphere responding, adjusting, redistributing that energy across the planet. These are not isolated facts. They are movements within a single system. And when you step back, you can feel the coherence of it, the way each part connects to the next. What began as a question, a possibility forming beneath the surface, has unfolded into an understanding of process, of how something begins, develops, peaks, and eventually returns to balance. And even though the outcome of this particular moment is still unresolved, the structure of the system is no longer unfamiliar. It has become something you can recognize, something you can follow without needing to hold every detail at once. This is where the story begins to settle, not into an ending, but into a sense of completeness, where the journey of understanding becomes more important than any single conclusion. The patterns we have explored are still in motion, still evolving, but the way we relate to them has changed from curiosity to comprehension, from uncertainty to awareness. And in that awareness, there is a quiet stability, a sense that even as the system continues to change, the underlying principles remain constant, providing a foundation that does not shift with every new signal. This does not remove uncertainty, but it changes its role, from something that disrupts understanding to something that coexists with it, part of the natural variability of a system that is always in motion. As we move into the final chapters, the focus will continue to soften, shifting from explanation to reflection, allowing the knowledge we have gathered to settle into something quieter, something that can be held without effort, like the memory of a landscape that no longer needs to be described to be understood. There is a kind of ease that comes when we stop trying to direct our attention too tightly, when we allow what we have learned to exist without constant analysis, and simply let the system be what it is. The climate does not need to be controlled, to be understood, does not need to be reduced to certainty to have meaning. It exists as a continuous flow of interactions. You're always adjusting, always balancing, and our role in this moment is not to force it into clarity, but to observe it as it unfolds. The signals we have followed, the warmth beneath the surface, the shifting winds, the alignment of patterns across distant oceans, they are still there, still moving, but now they can be held more lightly, not as questions demanding answers, but as processes that will reveal themselves in time. This shift from analysis to observation is subtle, but it carries a different quality, one that is less about effort and more about presence, about being aware of what is happening without needing to define it immediately. In this space, understanding becomes quieter, less verbal, more intuitive, a sense of how things fit together rather than a list of explanations. And in that quiet understanding, there is room to rest, to allow the mind to slow down, to release the need to follow every detail, and instead trust that the larger pattern is still there, still moving, even when we are not actively tracing it. The ocean continues its motion, the atmosphere continues its flow, the system continues its cycle, and we, for a moment, can step back from the mechanics and simply be present with that continuity. In the next chapter, we will move gently toward the close of this journey, allowing the patterns we have explored to fade into a broader sense of perspective, where the details soften and what remains is a quiet awareness of the system as a whole. If you step back far enough, beyond the data, beyond the timelines, beyond even the idea of prediction, what remains is a single image, a planet turning slowly, oceans moving in vast, quiet currents, air flowing in patterns that wrap around the globe, everything connected, everything in motion, yet somehow balanced within that motion. From this distance, the details soften. The numbers that once felt precise become part of a larger texture. And what you begin to notice instead is continuity. The way the system persists, adapting, shifting, but never breaking from its fundamental rhythm. The signals we followed, the warming waters, the shifting winds, the alignment across oceans, are still there, but they are no longer urgent. They are part of the ongoing story of a system that has always been changing, always finding new configurations within its boundaries. There is something calming in that perspective, not because it removes uncertainty, but because it places it within a larger context, showing that uncertainty is not disruption, but variation, part of the way the system explores its own possibilities. And as you hold that view, the need to resolve every question begins to fade, replaced by a quieter awareness, a sense that understanding does not require control, only attention. The earth continues its motion. The oceans continue their cycles. And whatever this particular moment becomes, it will do so as part of that larger flow. In the next chapter, we will bring that perspective gently inward, allowing the awareness of the system to settle into a more personal space, where observation becomes stillness and understanding becomes something you can rest within. As the larger view settles, something else becomes noticeable, a stillness that exists not outside the system, but within it, a quiet center that remains even as everything around it moves. The ocean currents continue, the winds shift, The temperatures rise and fall, but beneath all of that motion, there is a steadiness, a sense that the system is not chaotic, but structured, not random, but guided by principles that hold it together. When you bring your attention to that steadiness, the experience of observing the system begins to change. It becomes less about following movement and more about sensing continuity, the way each change fits within a larger whole. This is where understanding becomes something you can feel as much as think, a recognition that even complex systems have an underlying order, one that does not need to be forced into clarity, because it reveals itself naturally when given space. The signals we have explored are part of that order, expressions of how the system balances energy, redistributes heat, and moves through its cycles, and now they can be held more gently, not as problems to solve, but as patterns to observe. In this space, the mind can begin to slow, letting go of the need to analyze every detail, allowing the knowledge to settle into something quieter, something that does not demand attention, but supports it. And as that happens, the boundary between understanding and experience softens, because what you know about the system becomes part of how you perceive it, part of the stillness that remains even as the details fade. In the next chapter, we will move toward the final moments of this journey, letting the patterns dissolve into a calm awareness, where the story completes itself, not with a conclusion, but with a sense of quiet completion. As we reach the final moments of this journey, there is nothing new to add, nothing more to explain, because everything that needed to be seen has already unfolded, not as a single conclusion, but as a process that now begins to soften at the edges. The details that once held your focus, the movement of warm water beneath the surface, the shifting winds, the alignment across distant oceans, they are still there, but they no longer ask for your attention in the same way. Instead, they settle into the background, becoming part of a larger awareness, something you understand without needing to follow step by step. This is where the pattern begins to fade into quiet, not disappearing, but dissolving into the broader sense of the system as a whole, where individual signals are no longer separate, but part of a continuous flow. And the ocean continues its motion, steady and unhurried. The atmosphere continues its circulation, invisible yet constant, and the planet moves forward in its rhythm, unchanged in its essence, even as its details evolve. There is a calm in recognizing that this process does not depend on observation to continue, that it exists on its own terms, unfolding whether we are watching or not. And in that recognition, there is permission to let go, to release the need to track every change, to simply allow the system to be what it is. The understanding remains, but it becomes quieter, less active, more like a memory than a task, something you can return to if you choose, but do not need to hold on to. And as that happens, the mind follows, slowing down, settling into the same rhythm, no longer moving from question to question, but resting within the space that the understanding has created. Now, as everything softens, you can let your attention drift even further, away from the details, away from the patterns, into the simple awareness of stillness, the ocean, the atmosphere, the entire system we have explored continues its quiet movement, but you no longer need to follow it. You can rest, knowing that the story has been told, that the process has been understood, and that whatever comes next will unfold in its own time. There is nothing left to solve, nothing left to anticipate, only the gentle presence of a world in motion, steady and continuous. Your mind can slow with it, easing into the same calm rhythm, letting each thought pass without holding onto it. Just as the currents pass through the ocean, just as the winds move across the sky, the space around you feels softer now, quieter, as if the boundaries between thought and rest are beginning to dissolve. You can feel the weight of the day lifting, replaced by a sense of ease, of quiet completeness. The patterns we followed are no longer active. They are simply there, part of a larger whole that continues without effort, and you, for this moment, can step outside of it, into rest, into stillness. Let your breathing slow, let your thoughts drift, let the awareness of the system fade into the background, until all that remains is a gentle calm. The universe continues, the oceans move, the atmosphere flows, but you can rest now, held within that quiet continuity. Good night, sleepy universe. If this journey through the quiet patterns of our planet helped you slow down, even just a little, and then let that feeling stay with you as you rest. The ocean will keep moving, the atmosphere will keep flowing, and the story we followed tonight will continue unfolding long after this moment. You don't need to hold on to it. Just let it drift. If you'd like to return here again, to rest, to think, or simply to listen, you're always welcome in this sleepy universe zone. And if you feel that someone else out there might need this same quiet space, a simple like or share helps this reach them gently, without urgency. For now, close your eyes, let everything soften, and allow yourself to sink a little deeper into calm. I'll be here when you're ready to wander the universe again. Good night.